Thank you. Thank you for Alice Barbaresco and the organizer for this invitation. Also, many thanks to Alice because she has introduced coadjuvant orbit on this morning. That will be the main topic of my talk. So I will try to explain what are the geometric structure of thermodynamics introduced by Jean-Marie Souriau, on how to extend it for machine learning, especially for what we call thermodynamic-informed neural networks on Lie group machine learning. I start with this quote by Vladimir Arnold. Every mathematician knows that it is impossible to understand an elementary course in thermodynamics. So it was very difficult. I remember my course on thermodynamics, and I have good notation in thermodynamics, but I have the feeling not to understand really the structure. I would like to dedicate my talk to Yvonne Choquet-Bruhat, who just passed away this week. She was the first woman elected at the French Academy of Science, and she worked a lot on geometry for physics, especially with André Lichnerowitz and Jean Leray, which has the French school of geometry for physics, and especially his book, Analysis, Manifold, and Physics. And I invite you to look at this video at EHES for his 100th birthday, and also his conference on his collaboration with Einstein at the French Academy of Science. Also, the hero of today is Sadi Carnot. So we have just see the bicentenary of the book of Sadi Carnot, Réflexion sur la puissance motrice du feu. So we have organized Raphaël Pisano has organized in Lille a conference, Carnot Lille 2024. And the book will be edited by Springer on this conference. There is also a Maison Française d'Oxford. We have organized with also Raphaël Pisano, but also Robert Fox from University of Oxford, a meeting, a seminar on Sadi Carnot, and also at École Polytechnique, you have a Sadi Carnot Legacy conference organized by Goupil, Christophe Goupil, and at the dinner at Maison des Polytechniciens, the family of Carnot, so Olivier and Alix Carnot, have the good idea to launch a project is to place Sadi Carnot in the Panthéon, with Lazare Carnot, his father, and with his nephew, Sadi Carnot, the French president of the Republic. So Sadi Carnot is not so popular in France, more in UK, or so you could find a very good video of Michel Serres on Sadi Carnot, and I've just found a song on Sadi Carnot generated by AI. And only recently, in the last version in December of the French Academy of Science dictionary, they have added the fact that Sadi Carnot was the inventor of thermodynamics. And also, I was in Glasgow in November, and it corresponds also to the bicentenary of Lord Kelvin that has rediscovered the invention of Sadi Carnot and popularized this invention. And he was awarded by the Grande Croix de la Légion d'honneur by the French president of the Republic of this period for this rediscovery of Sadi Carnot book. But you could find also thermodynamics in Erwin Schrödinger, so I invite you to read the book Statistical Thermodynamics by Erwin Schrödinger. So my talk, I will give you an elementary symplectic structure of thermodynamics. So you have to remember only that. The other is mathematics development, but the main idea is in the first chapter. Then I will introduce the first idea by Constantin Carré-Théodory, was to try to use this Pfaffian form of thermodynamics to introduce an axiomatization of thermodynamics. It was in fact a contact structure, a contact geometry of thermodynamics. Then I will introduce information geometry because I need to introduce information geometry to make the link with the work with Jean-Marie Souriau, who has introduced symplectic foliation model via moment map of information geometry on what we call Lie group thermodynamics. And then we give a definition. This is the main topic of my talk, that you have a geometric definition of entropy. Shannon has given an axiomatic definition of entropy, but Suryo has given a geometric definition of entropy. And we will see that the entropy is a Casimir function in the coadjoint representation. So it is a constant function on the coadjoint orbit on the symplectic leaf. So I will explain hereafter. During the seminar, you have a talk by Baptiste Coquino, because in the second part, I will address dissipative phenomena on the link with metriplectic flow. So Baptiste has explained you in the seminar. You could see the video on the seminar channel, that the metriplectic flow is compliant with the Onzinger relation in thermodynamics. And then we will study the transverse symplectic foliation structure. And I will conclude with some extension with the link with the Liouville complete integrability of information geometry and the application for thermodynamic-informed neural network. Okay, the structure. What is very important in physics is equivariance, as explained by Alice. And I invite you to read this paper. It is a white paper done by Berkeley, MIT, Yale, Princeton on symmetry group equivariant architecture for physics, which is the main basic tool of now many development and modelization in physics, but also now in machine learning. The main tool I will use will be the coadjoint orbit. So the coadjoint orbit has been introduced by Kirillov. So Alice makes reference to Kirillov, Constant, Suryo, two forms. So Kirillov has introduced in this book elements of the theory of representation. So it is a representation of Lie group. So this is a Russian school which has introduced first this tool. And here you have a testimony of Jacques Dixmier on the work of Kirillov. And he says, Kirillov thesis, published in 1962, immediately aroused a great deal of interest. Kirillov quickly convinced himself, and he convinced the mathematical community, that this orbit method should be applicable to groups much more general than nilpotent groups. So we will see what are the roots of Lie group thermodynamics. We have two roots. So you have the classical axiomatic roots with Bourbaki and set theory and also category theory. So information geometry has been extended by a Russian Nikolai Chentsov in the framework of category theory. And Jean-Louis Kozoul has introduced some structure with Lie algebra homology, which are the basic bedrocks of information geometry. But you have another path, which is based on symplectic geometry with Jean-Marie Suryo, who has introduced the tool of symplectic geometry in mechanics, and also the tools introduced by Charles Erechman and George Reb on foliation and webs theory. So foliation, feuilletage in French, and webs is tissu in French. And so Jean-Marie Suryo has introduced Lie group thermodynamics. It is in fact an extension of information geometry for Lie group. And in Thales, we have made the link with information geometry, because there is no information geometry in the Jean-Marie Suryo book, and also the link to metriplectic flow for dissipative phenomena. And then you have new tools for Lie group machine learning and thermodynamic-informed neural network. Okay, so my talk will talk about Lie group and Lie algebra representation theory. So you have the notion of Lie algebra homology, coadjoint orbit, cocycles, and it could be extended also for quivers. Obviously, symplectic geometry and Poisson geometry, and we will introduce the KKS2 form, Constant, Kirillov, Suryo 2 form, and the moment map, the main invention by Suryo. So moment map is a geometrization of Noether theorem. It is also linked to integrable system, because in fact, information geometry and statistical manifold are linked to complete integrable system. And so there is a recent connection between information geometry and Delzan polytope theory. You see the link with foliation theory because we will give a foliation interpretation of thermodynamic and information geometry. Information geometry itself, but I will introduce this information geometry with Kosul tool. So Jean-Louis Kosul was a PhD student of Henri Cartan, but he has developed the theory of Élie Cartan on homogeneous domain of the geometry of symmetric homogeneous bounded domain. First, very simple example is Poincaré hyperhalf plane or Poincaré unit disk. And we will see how to use it for, with natural gradient in machine learning. On metriplectic flow, so here we extend the classical model of Suryo for dissipative phenomena. So it could be a very interesting also topic for machine learning because for the time being, machine learning only use non-dissipative phenomena on what we call gradient of learning is simple symplectic gradient, which is not dissipative. Yes, and I will make the link with Philippe Morrison on Baptiste Coquinot work to make the link with Onzinger relation. Obviously, you can put all of that in the context of calculus of variation on the Suryo-Lie group thermodynamic. So about dissipative, non-dissipative. So main phenomena could be reduced to by capturing the symmetry on the invariant of the problem by a Poisson bracket, so as explained by Alice with Poisson geometry. So you can reduce the classical Hamilton equation to this dynamic with Poisson bracket, but this Poisson bracket only describes a dynamics for non-dissipative phenomena. Philip Morrison has introduced during the 80s metriplectic flow, where you will add another bracket, but it is not a Poisson bracket, it is in fact a metric flow bracket. And so you have two brackets now, a Poisson bracket to describe a dynamic of non-dissipative phenomena, and dissipation is given by this bracket. In my notation, H will be the energy, S will be the entropy, and we will see that this metriplectic equation, as explained also by Baptiste Coquinot, preserves the first principle, so it is the quantitative preservation of energy, and the second principle of thermodynamics, which is the qualitative degradation of energy, or entropy production. Yes, so what is metriplectic? Metriplectic is an aggregation of two terms, metric and symplectic. So in fact, you will have the metric term and the symplectic term will give you this metriplectic equation with two characteristics, is why I've made the first time the connection with the Lie group thermodynamic of Suryo. For this model, you should have that the entropy is a Casimir function of the Poisson bracket. And the energy, H, is a Casimir function of the metric bracket. Okay? So it's very simple to interpret. In fact, you have two foliation. You have a symplectic foliation, which are the Lies, which correspond to the coadjoint orbit. So the coadjoint orbit will generate this symplectic foliation, and Suryo has observed that in fact the entropy is a Casimir function on this coadjoint orbit. So it means that the entropy is a Casimir function of the symplectic Lies. And when you move on this leaf, on this foliation, you use the Poisson bracket. But if you want to describe dissipation, dissipative phenomena, you have to use the other term, so in red. So you will have a transverse dynamic to the symplectic foliation, and you have another foliation, which is not a symplectic foliation, but a Riemannian foliation. And also, this is very interesting because it corresponds to the level set of energy, okay? So when I understand this structure, I think I have understood the thermodynamic for the first time. You have two foliation, one foliation which is a symplectic foliation level set of entropy, and a transverse foliation which is a level set Riemannian foliation, level set of energy. And you can describe all dissipative phenomena in this way. Okay, also in thermodynamic-informed neural networks, they use these two constraints to preserve the first principle of thermodynamic and the second principle of thermodynamic. I will come back to that. So the only thing that you have to remember to my talk is this definition of entropy. Entropy is the invariant Casimir function of Lees of symplectic foliation associated to the coadjoint orbit generated via moment map of symmetry group acting on the system. So I will try to explain this definition. But this is a definition of a Casimir function. S is the Casimir function, is for all Hamiltonian H. The Poisson bracket SH is equal to 0. Okay, so here S is the entropy. H could be any Hamiltonian or the energy. And Q is the heat. We'll see Q will be an element of the dual of the Lie algebra. I put in index theta tilde, which is related to co-cycles. So Alice has presented some model where you have equivariant action, equivariance of the coadjoint operator, but in some case, the coadjoint operator is not equivariant, and you have an additional term, and you have to modify the Poisson bracket to take into account what we call a default of cohomology of the group. And this is this is the same expression written in another way with the coadjoint operator in the Lie algebra. The derivative of the entropy with respect to the heat will be the Planck temperature, we will see hereafter. But here you could see that you have only two variables, the entropy and the heat. And you have some method to build from this equation the Casimir function. Okay, so the idea, yes? This is a Poisson bracket. The metric bracket. I will give the definition hereafter, okay? This is a symmetric positive definite bracket, okay? Because it is linked to a Riemannian foliation, okay? And you have also, to make the link with information geometry, to this foliation will be linked to the Fisher metric, but extended by Souriau for Lie group thermodynamic. And the other way is the dual of the Fisher metric, which is the Hessian of entropy. So you have two dual metric given by information geometry. So this is our proposal to replace the channel definition of entropy, which is purely axiomatic, by a geometric definition of entropy of Souriau. So it's not so obvious. In Souriau, you have this equation. No, not this one. I will see you hereafter. It was okay. So the first time I find the equation is not in the book of Souriau, but in a paper of Souriau. You have this equation. Souriau writes, it is obvious that. So we take 2 months with Charles-Michel Marle to try to demonstrate that it is right. But this equation is this equation. So Q is the heat, beta is the Planck temperature, usually, the inverse of temperature. Z is an element of the Lie algebra. Theta T is a co-cycle in case of non-null cohomology. So I try to put the Carnot cycle on the foliation. Okay, you are familiar with the Carnot cycle, but you can rewrite in the volume on pressure and temperature, but you can rewrite the Carnot cycle in the parametrization of entropy and temperature. And in fact, here you have a constant also heat, Q1 and Q2. And in fact, you have a thermodynamic modification at a constant entropy, then at a constant energy, and then constant entropy and constant energy. Okay, so this is a Souriau co-cycle interpreted in the foliation model. Okay, is it clear or is it completely obscure? So it's very simple in terms of symplectic geometry and Poisson geometry to interpret thermodynamic like that. So in the yes. Yes, I'm not so excited by the Kuiper-Leiber entropy. In fact, when I will introduce you information geometry, I will use causal structures. The history of information geometry introducing Kuiper-Leiber as an initial equation to introduce a Rao Fisher metric is not a good way. In fact, I will explain after. But we should be able to extend Kuiper-Leiber geometry. I will explain you. You have to replace the classical Laplace transform to a Laplace transform on symplectic manifold, which is obvious for mathematicians. This is their work during the last century, how to define a Fourier transform on Lie group. So I will give you the equation. So, yes. We'll explain you in hereafter. So here you have three theories. You have a first theory, which is a Sorio-Lie group thermodynamic with entropy as a Casimir function, and also information geometry introduced by Jean-Louis Causoul. I will give you the... So Jean-Louis Causoul was also a member of Bourbaki group of the second generation. And so Onzinger, the relation with metriplectic for dissipation, and Baptiste-Coquinot has explained in the seminar the link between metriplectic flow and Onzinger relation to validate that the metriplectic flow is a good flow. And the last one is Reeb foliation on theory and symplectic foliation, which has been introduced by Charles Erechman and Georges Reeb. Okay, so we have launched a seminar which is called Nord-Bassin Parisien Seminar, but it is a seminar between Nancy and Strasbourg, and also our colleagues from Belgium. And we make reference, this is small seminar compared to Sud-Rhodanien seminar, but during the 80s, they have launched Sud-Rhodanien seminar between Lyon, Marseille, and Montpellier, working on symplectic geometry and mechanic, foliation and geometric quantification, symplectic geometry and contact geometry, Riemannian foliation, singularity foliation and Hamiltonian mechanics. So you can find at Herman I'll make a new edition of this seminar. So in this seminar, we have discovered three publications: Géométrie du moment, Geometry of Moment Map by Condevaux, Dazer, Molino, Gamma Structure, so Poisson Gamma Structure and Lieberman Foliation by Dazer and Molino, and Symplectic Duality, Foliation and Geometry of Moment Map by Molino. And in fact, these transverse structure are linked what is called also gamma structure and also a Lieberman foliation. So at the beginning of thermodynamics, they try to understand what are the geometric structures. This is here you have Josiah Willard Gibbs diagrams sculpted by James Clerk Maxwell. Try to understand what is the geometric structure of thermodynamics. And also in Carnot, you have some ideas that also if you have to consider when bodies are in motion, what are the impact on the thermodynamic. And also Charles-Michel Marle gives me this remark that in the book of Gibbs, you have this idea that the generalization of Gibbs state built with a moment map as a product of the one-dimensional group of translation in time and the three-dimensional group of rotation in space for the study of systems contained in a rotating vessel. So this is the main idea of Souriau that I will explain, that classical thermodynamics is valid only for one group, time translation, okay? But if you look for a centrifuge, you cannot apply classical thermodynamics. So the main idea of Souriau, could we define a thermodynamic which is covariant under the action of the Galileo group? It was his first question. So this idea to take into account the covariance with respect of the Gibbs state with respect to a group, or especially a translation and rotation group, was in the book of Gibbs. During the beginning of the end of the 19th century, so Karateodori tried to axiomatize the thermodynamic on using the FAV form. So I will not have 2 times to explain this part, but the main idea, so it's very difficult to read the paper of Karateodori, but I invite you to read the lecture of Wolfgang Pauli, which has rewrite this model of Karateodori in a more clear view. And it has been only recently interpreted that the model of Karateodori is a contact geometric model of thermodynamic. Okay, so contact geometry is very interesting, but so you are in dimension 2n plus 1, but you can simplify this model to have a 2n plus 2 dimension, and then to have a symplectic one. So I will not give too much detail, but I give you the reference of Theodor Frankel, the geometry of physics, where he interprets the Karateodori model as a contact geometry. Recently, I have discovered, I don't know if you know Herbert Callen. If you want to learn thermodynamics, you have to read the book of Callen. Roger Ballian said me that there is only one book in thermodynamics, the book of Callen, and after his book, but and I have discovered that he has written 2 papers during the 70s, a symmetry interpretation of thermodynamics and thermodynamics as a science of symmetry. And he gives this idea of Souriau, but he was not aware of the Souriau work. So symmetry under spatial translation implies conservation of momentum, and rotational symmetry implies conservation of angular momentum. It's relevant as the thermodynamic coordinates underlies the first law of thermodynamic, time translation, spatial translation, and spatial rotation symmetries are interrelated in the single class of continuous space-time symmetries. The symmetry interpretation of thermodynamics immediately suggests that energy, linear momentum, and angular momentum should play fully analogous roles in thermodynamics. The main idea that we will explain with Souriau, you have a group acting on your thermodynamic system. So you take the Galileo group, is a time translation, space rotation, and you want that your Gibbs state should be covariant under the action of this group. Okay, this is not the case for classical thermodynamics, because the classical thermodynamics is only covariant under the action of time translation. Okay, information geometry. So the main idea comes from Fréchet, in fact. So I'm very happy of this figure, of this picture I found it at ENE, École Normale Supérieure. This is a very young picture of Fréchet at École Normale Supérieure. And in a paper of 1943, he has introduced what we call the Cramer-Rao bound. But you have many more in this paper, but only written in French. And he says that the main content of this paper is in this lecture at Institut Henri Poincaré in winter 1939. It was not a very good period to write a paper. So I will not give you a detail, but I have written deeply this paper, and you have the structure of Fischer metric. And also, he has discovered the Legendre transform existing for density of maximum entropy. So I invite you to read this paper. And after Russian school axiomatize the foundation of information geometry, and I make a reference to Nikolai Nikolaevich Chentsov. So classically, we introduce information geometry by this way. So you have a density of probability parameterized by theta. And the idea of Rao is to find a metric which is invariant by change of transformation, parameters transformation. So you take the Kullback-Leiber divergence between p theta and p theta plus d theta, you make a Taylor expansion, the first term cancel, and the second term make appear what we call the Fisher matrix, which is given here, okay? And this Fisher matrix is used as the inverse, as a lower bound of the covariance matrix of the statistical estimators. So if you apply that for Gaussian law, it's very simple. So the Fisher matrix is diagonal. And if you apply the computation of the Fisher-Rao metric, you have this one. And if you are familiar in hyperbolic geometry, you observe that it is a metric of upper half plane of Poincaré. Okay? Why? Because the mean is real, the standard deviation is positive, so the space of parameter of Gaussian density is in the upper half plane of Poincaré. So it's obvious that we will recover the metric of Poincaré. And here, in the model of Rao, is that you take into account that the variance on the mean is sigma 2, and the variance on estimation of sigma is sigma 2 divided by 2. So you cannot integrate this metric, so this is a famous idea of Poincaré, so to complexify the plane and to use a Cayley transform to transform the upper half plane of Poincaré to the disk of Poincaré. So you are now a new variable, W, given by the Cayley transform. You can no longer integrate, but Poincaré integrate from the middle to a point on the radius, and then use the isomorphism of the Poincaré disk to have the general formula. So what is the main idea is when you have a Gaussian, you can represent it by one point in the Poincaré disk. Okay, if you have a second Gaussian, you have a second point. And the Rao-Fisher distance, information geometry distance, will be the geodesic in the Poincaré unit disk. Okay, and this is a link with Jean-Louis Causul work, because Jean-Louis Causul work on homogeneous bounded domain, and the most simple example is the Poincaré unit disk. The question of Elie Cartan to Jean-Louis Causul is to try to define a metric which is invariant by all the automorphism of this space. If you are familiar with information geometry, also we use a natural gradient. So we apply the Fisher matrix, the inverse of the Fisher matrix, to have a gradient of learning which is invariant by change of parametrization. And during the last decades, Yann Olivier has extended this natural gradient to define a natural Langevin dynamic, mixing the natural gradient and the stochastic gradient. And we give him the GSI base paper award for this work. The natural gradient is used. I found recently that Google tried to use the natural gradient for LLM also. So you have this paper using this natural gradient to improve LLM on convergence of LLM. So now, symplectic foliation via moment map on causal Fisher metric from information geometry for Lie group thermodynamics. So I enter in the work of Souriau. So in 2019 has been organized in Paris a congress for the 50 birthday of his book, Structure des systèmes dynamiques, Structure of Dynamical System. And Jean-Pierre Bourguignon has given testimony on the discovery of this book when he was young student at École Polytechnique. And they have put in place a seminar of young students because they consider that the lectures on mechanics at École Polytechnique during this period was not so good. And they have discovered this famous book of Souriau, and all was so clear with this book. So Jean-Marie Souriau was graduated from École Normale Supérieure in 1942, and in 1942 you have also Jacques Dismier, which is also very well known for developing algebra, and also René Devez for forme quadratique et groupe classique. So in 1969, he has written this book, Structure des systèmes dynamiques, where he has introduced symplectic geometry in mechanics. But in chapter 4 of this book, was dedicated to statistical mechanics. And I think that nobody has written this book during this period because it was read only by people from geometric mechanics. And I have made the link with Jean-Louis Cauzoul. So we have discovered lectures given by Jean-Louis Cauzoul in China. And we have convinced Springer to make the translation of this book, which is Introduction to Symplectic Geometry, where you have the theory of Souriau, which is explained in modern notation, because the book of Souriau is very difficult to read, because it uses its own notation for Lie group. So we can read this sentence. These formula are universal because they is involved only the symplectic manifold. The Lie group is cocycle, is symplectic cocycle on the couple, the heat and the temperature, the temperature and the heat. And he calls that thermodynamique des groupes de Lie, Lie group thermodynamique. Okay, so what is it? It is, in fact, a symplectic theory of heat. So you know Fourier theory of heat, Clausius mechanical theory of heat, or Poisson mathematical theory of heat. But Souriau has introduced a geometric theory of heat and a symplectic theory of heat. A translation has been made in English, Structure of Dynamical System, a symplectic view of physics. So why I read this book? Because in this book, you have this property. The total mass of an isolated dynamical system is a class of cohomology of the default of equivariance for the moment map. So it could be very obscure, but it used to say that the mass in classical mechanics is a geometric object due to the cocycle of the default of cohomology of the Galileo group. Okay? And in relativity, you have not that because the Poincaré group in relativity has no default of cohomology. It's why the mass don't play the same role in classical mechanics and in relativity. But I read especially the chapter 4, where he develops the Lie group thermodynamic. So what he says, so you have some trumpet in the book of Souriau. Each time you have an important theorem, you have a trumpet. No, it just say in French, I will translate you, but that the classical thermodynamic on the Gibbs density is not covariant under the action of the Galileo group. This is a first remark of Souriau. And what did he do? He proves that, in fact, the Planck temperature, so the inverse of temperature in thermodynamics, is an element of the Lie algebra of the group acting on the system. And the heat is an element of the dual of the Lie algebra. Generalize the notion of entropy as a Legendre transform of minus logarithm of the Laplace transform, and has a Casimir function on symplectic cleave. And also he has extended, without knowing information geometry, he has introduced a metric for Lie group because he has defined a statistic of Lie group. And so it is an extension of Fisher metric for Lie group. And he has made the analogy with, he calls that, we will see that the Fisher metric could be interpreted as what we call a calorific capacity in thermodynamics. Okay, so the main formalism of Souriau is fully covariant with no special coordinates, and you have the covariance of the Gibbs density with dynamic group. He has also developed this theory in another paper, 1974, Statistical Mechanics, Lie group, and Cosmology. And the first part is dedicated to symplectic model of statistical mechanics. So it is in French, so I have translated, we have organized at Léouche a seminar, and I have a paper on Springer book of the proceeding of the seminar, where I have translated 3 papers of Souriau in English, developing this theory. Okay, so all is based on symplectic geometry. It's a long history of symplectic geometry. The main idea of Souriau is that the main idea comes from Lagrange, because Souriau was has the first position at Institut des Études de Tunis, and he lives in Carthage, and he has nothing to do with many people from not from science, and he decided to read the Lagrange book, and he has discovered symplectic structure in Lagrange. And so you have different contributors to symplectic geometry, and if you are interested, I have given at a Mamufy seminar a link to this history and discovery of this symplectic structure. And obviously, Souriau was a PhD student of Lichnerowitz, which was the main actor during this period at Collège de France. And we will make the link also with the work of Paulette Lieberman. So it was very well known because at the beginning he was invited by Erechmann and Lichnerowitz at the first Congress in Strasbourg, which is very well known in 1973. So in the background you have Jean-Marie Souriau, which was invited, and here you have Jean-Louis Cozoul, but you have many famous and the most famous geometers of this period. So what is the main idea? The main idea of Souriau is very simple. So take the Newton equation. Okay, here you have the Newton equation. R is the position, M mass, F force. So you have the Newton equation. You can rewrite with the variable the speed, derivative of position by t, by the time, and you have another equation. So you have two equations that you can rewrite by a system of two equations. Okay. On this system of equation in a new space that is called evolution space. So time, position, speed, you have two equations that form a Pfaffian form system. And this Pfaffian system will generate a foliation. And what has observed Souriau that you can introduce to a second order tensor, sigma, that is called the Lagrange-Souriau form, that is now called the KKS2 form, Constant-Kirillov-2 form. So he makes only one reference in his book, is François Galissot, Les formes extérieures en mécanique, his PhD in Chartres in 1954. So Galissot tried to find, give this theorem. There are only three types of differential form generating the equation of material point motion. And you have this form A, form B, and form C. And Souriau has used this form B. So it is always the same idea to be invariant by the action of the Galileo group. Okay, we'll skip that. So, I will skip that also. So I will use this notation. Sometimes it's not the same notation in the book, on papers, on coadjoint orbit. So I define the coadjoint orbit by duality bracket with this notation. So you have a genus -1 here. Not a problem. So as introduced by Alice this morning, so you have the adjoint operator. The adjoint operator is the action of the group on the Lie algebra. And you have, by duality, you can define a coadjoint operator will be the action of the group on the dual of the Lie algebra. Okay, and what is important, as explained by Alice, is the coadjoint orbit. So you take G, an element of G, and for all G, an element of the Lie group, you look at the action of the group on the dual of the Lie algebra, and you will generate this coadjoint orbit and this foliation associated to the coadjoint orbit. So you can introduce a two form, which is called KKS2 form, Constant-Kirillov-Souriau. And what is the main idea of Souriau? This is an idea that you have in Lagrange. If you want to make statistics on the movement of planets, the idea is that take a group, the Lie group acting on your system, take the coadjoint orbit, and associated to this coadjoint orbit, a symplectic structure with this two form, the KKS2 form. Okay, so you have one point in the space of Lie group, and you will put this point on the symplectic manifold. In this structure, this group acts homogeneously on this homogeneous symplectic manifold. So obviously, if you want to make statistic on the group, the idea of Souriau and Lagrange is to make statistic on the symplectic manifold. Okay, when you have some element in the Lie group, you want to make a statistic, you want to define some mean or variances for the Lie group, all is in the coadjoint orbit. Okay, so this is the main advantage of artificial intelligence, that we can make moving Jean-Marie on Jean-Louis Kozoul. So I come back to information geometry. The good structure for introducing information geometry is this one. You have to introduce phi, which is a generating function of cumulant, okay, minus log of the Laplace transform, with lambda is a Lebesgue measure. And if you take the Hessian of this function, you will find the Fisher metric. But the other relation is that the Legendre transform of this function, given by this one, you have to define a duality bracket. This gives you the entropy. So the entropy, the Shannon entropy, will be the Legendre transform of this function. In fact, this relation has been introduced by François Massieu. François Massieu was an engineer from Corps des Mines, and he has discovered this relation, and we call that the Massieu potential. Be careful, this is not the time I give lectures. I want to kill the free energy. The free energy is not the good potential. Okay, so classically people use free energy. Okay, so free energy will be energy minus temperature by the entropy, but in fact you have to use the Massieu potential, which is this one. You have to divide it by the temperature, and so yes, that's right. Okay, I could rewrite this way. Okay, and here you have the Legendre transform between this variable, which is the Planck temperature, the energy, the Massieu potential, and the entropy. Okay, so you have to stop to use free energy, because when you use the free energy, you broke the structure and you have no longer the Legendre transform. So this is a mistake of Gibbs and Duhem to have used this kind of potential, and the good potential are the Massieu potential. So if you are interested, there is a very good paper of Roger Ballian on the website of the French Academy of Science about Massieu potential. So you have two systems of coordinates which are dual to each other. Okay, what is important is this structure: Legendre transform on two dual coordinates and two dual potential. The Massieu potential and the entropy. Okay, so Kozoul has extended that now. So you are here. You are on R. But for Kozoul, he has studied on a sharp homogeneous sharp cone, sharp convex cone. So omega is a sharp convex cone, but it is exactly the same relation, minus log of the Laplace transform on this sharp convex cone. And the question of Kozoul is, what is the metric which is invariant by all the automorphism of this cone? Okay. Yes. No. Yes. And so it has also been studied in Russia by Ernest Weinberg, and we talk about this function, which is the Kozoul-Wilberg characteristic function. You know the characteristic function of probability, but the history of characteristic function of probability is that Poincaré gave a lecture on thermodynamics, and as he was graduated from Corps des Mines, he takes the book of Massieu, and he has discovered the Massieu potential, and then he gives the idea to Poincaré to introduce characteristic function in probability. And then Poincaré gave a lecture at Sorbonne on probability, and he introduced characteristic function with the idea of Massieu in thermodynamics. And so Kozul proves that the only metric which is invariant on this sharp convex cone, which is invariant under the action of the automorphism of the cone, are given by the Hessian of the log of this function. So it is exactly the Fisher metric in information geometry. Okay. On Suryo, it's exactly the same structure. We have not changed the structures. You have a new potential, but now the Laplace transform is no longer on a sharp convex cone, but M is a symplectic manifold. On U here is a moment map invented by Suryo. So it's a map from the symplectic manifold to the coadjoint orbit, which is in the dual Lie algebra. And you have now the Legendre transform, but now the two variables, Q will be the heat, will be an element of the dual of the Lie algebra, and beta, which is a Planck temperature, classically, is an element of the Lie algebra. Okay, so here, all is geometric. Q is an element of the dual of the algebra. The temperature, the Planck temperature is an element of the Lie algebra, and we will see that the entropy will be a Casimir function of the symplectic leaves. And I say, yes, this is very successful geometric description, and I discussed with Jean d'Ombre, which is a biograph of Fourier, and finally we have concluded, no, this is just an extension of analysis. So this tool is the extension of the Fourier transform on Lie group. This is a work of last part of the last century. They have extended Fourier transform on Lie group, and if you could extend Fourier transform on Lie group or Laplace transform on Lie group, you will be able to define that, which is also purely analytic. Okay, so in Suryo, he introduced this metric. So the first time I read this metric, it was very difficult. Well, if you are a geometer, this tensor, this one is classical because it is linked to the KKS2 form. So this part is linked to the KKS2 form. But you have an additional term which is linked to the cocycle. So Suryo introduced this tool, the moment map, so from the symplectic manifold to the coadjoint orbit, so the dual of the Lie algebra. And this moment map is a geometrization of the Noether theorem. Okay, Noether theorem, you have a symmetry, you have an invariant. Moment map, the component of the moment map are the invariant of the Noether theorem. But in sometimes, when you have a default of cohomology, G, indexed by the Lie bracket of xy, is not equal to the Poisson bracket of gx, gy. Okay? And so you have an additional term, and you can make the link to the theta tilde to theta, which is a cocycle. And also, you have if you take, yes, and the other relation is this one, where the cocycle appear. That proves that the coadjoint operator is not equivariant. If the coadjoint operator will be equivariant, you will not have this term. But when you have an affine coadjoint operator, you have an additional term, which is called the Suryo cocycle. Like that, Suryo cocycle. So, okay, Q is indexed by beta. When you have the action of the group, you have the adjoint operator, and the Q adjoint G beta is coadjoint operator JQ plus a cocycle. Where? No, you have no beta. On Q is indexed by beta. Q is parameterized by beta. So beta is the Planck temperature, Q is the heat. So you have all the demonstration in my slide, but I will not give the detail. Now, what is important is that the metric introduced, you can prove that the metric introduced by Suryo is the Hessian of the Massieu potential. So it proves that it is the Fisher metric for Lie group. So you have two figures in the book of Suryo, which are interesting. This one, so we say you have the Lie algebra, you have the group, and you have the dual of the Lie algebra. Beta is in the Lie algebra, so when the group acts, you have the adjoint operator, and Q is parameterized by beta, so you have Q adjoint beta. And if you take the action of the group on Q, Q is an element of the dual Lie algebra, you will have the coadjoint operator on Q. And when you have not equality, you have the coadjoint orbit. Okay, so this is a figure in the book of Suryo. And you have this fundamental equation of thermodynamics. And the second figure is also very interesting. Here you have the Lie algebra, so you have beta, is Planck temperature, an element of the Lie algebra. When the group act, you have the adjoint operator. Q is in the dual of the Lie algebra. When the group act, you have the coadjoint operator plus the Suryo cocycle. And here you have two functions, the Massieu potential and the entropy. The entropy, with a miracle, is invariant under the action of the group, and phi is not. You have a term which is proportional to beta, but it doesn't matter because the Fisher metric is a Hessian of phi, okay, with respect to beta. So this term will disappear, and the Fisher metric will be invariant under the action of the group. So why we will see why entropy is invariant under the action of the group. We will see this is a property of the Casimir function. So Suryo look for this kind of group, the Galileo group, if you are familiar with mechanics. So you have the two frames, X prime and X. And so here you have rotation, you have boost in speed, and you have space translation, and you have time translation. The idea of Suryo, you can rewrite this transformation with an additional dimension as a matrices. This is a theory of Lie group representation. And this matrices is a Lie group. Okay, so this is a Galileo group. But this group has a default of cohomology. The coadjoint operator is not equivariant for this group. And then in his book, he tried to find what is the Gibbs equilibrium for the Galileo group. So he proves that there is no equilibrium. Action of the full Galilean group on the space of motion of an isolated mechanical system is not related to any equilibrium Gibbs state. So his idea is to take a one-parameter subgroup of the Galilean group. So what is the idea? You can parameterize this group by the Lie algebra, okay? Exponential map of tau beta. Tau is a real value, and beta is an element of the Lie algebra, and you can parameterize the matrices by tau. And then you can parameterize all equilibrium, and you will take the most simple one, the centrifuge. It's very important to understand. I understood why the temperature is an element of the Lie algebra with this example. So you have a centrifuge. Okay, what are the equilibrium of the centrifuge? You have two equilibrium. You have a first temperature, which is a classical Planck temperature for thermal equilibrium. But you have another equilibrium, which is the wall. The wall is a reservoir of angular momentum. And each time you have a particle with a choke on the wall will transmit angular momentum to the particle. And with viscosity, you will have a second equilibrium, which is related to the angular momentum. Okay, so you have a thermal balance, thermal equilibrium, and you have angular momentum equilibrium. And so the particles are rotating in the centrifuge, and they homogenize their temperature. Okay, so when I said to Roger Ballion, this is a difficult problem, and he said, no, I have this problem solved in my book. But Roger Ballion, how Ballion compute the Gibbs density for a centrifuge? He said, okay, the energy should be constant, so it will give you the first hyperparameter of Lagrange, the Planck temperature. And he said, okay, we have also the angular momentum should be constant. And so I had a second hyperparameter of Lagrange for the second equilibrium, and I look for the maximum entropy density given by this equilibrium. But you see, you have to make some assumption and so on. In Suryo, the Gibbs density is given by this expression, where here is the moment map, and here is the Planck temperature. So you recover the classical thermodynamic if you take the Planck temperature. as beta is the derivative of the entropy by Q, you find ds equal dq divided by T, which is the Boltzmann-Clausius entropy. And the Gibbs density is equivariant under the action of the group. Okay, I will skip that. So I will conclude with two things. So the first thing is that the entropy, so I could, this notation is for affine equivariant coadjoint operator. You have this property of the entropy. That means, in fact, the entropy is a Casimir function of to the Poisson bracket. So Casimir was a PhD student of Niels Bohr on Ehrenfest, where we have developed this idea in his PhD thesis. Okay, and so you have just to introduce a good Poisson bracket. So the classical Poisson bracket is only this term, but when you have a co-cycle, you have to add this term in Poisson book. So you can extend for a default of cohomology. The first term is given by the structure coefficient, which is classical in Lie group. And the second one is given by the default of cohomology on the moment map. Okay, keep that. The detail of the equation. Yes, what is important is explain also the second principle of thermodynamics, because ds will be equal to theta tilde tensor, and the theta tilde tensor is only the Fisher tensor. And as the Fisher tensor is positive definite, you have the principle of thermodynamics, second principle of thermodynamics, which is explained by that. And you have a new equation, which is the Euler-Lagrange equation of heat. This is a Fourier equation written geometrically, okay? But with the heat, in Fourier, you can write the heat equation on the temperature on the heat. Here you have the heat equation in the model of Souriau. Okay, so with François Gebelmaz, we have also studied the stochastic model of this part. And you recover the famous Poincaré papers, where you have the Euler-Poincaré equation, which is given here, which is exactly this one, because Q is a derivative of phi, and it is exactly the equation of Poincaré. This is the Euler-Poincaré equation for the problem of variational problem. Okay, I skip that. So you will find an example, because it's very theoretical, but you can take a group. So a very simple question: what is the Gaussian density in the Poincaré unit disk? Okay, it's a very simple question. What is the Gaussian density in Poincaré unit disk? The Gaussian density is the density of maximum entropy. So it is given by the model of Souriau. In the Poincaré unit disk, a group act, it's SU11. So you compute the Lie algebra, you compute the dual of the Lie algebra, and the moment map is given by this expression. Okay, so the symplectic manifold is here the unit disk of Poincaré, and the coadjoint orbit generated by the moment map are this hyperbolic sheet in green. Okay, this is the example of the coadjoint orbit. So I invite you to read this paper of Charles-Michel Marle interpreting this. So moment map is from Z is an element of the unit Poincaré disk, and the coadjoint orbit is an element of the dual of Lie algebra, because you can decompose on the dual of the Lie algebra bases. And if you look at the three components, you have this relation, which are the hyperbolic sheet of the system. And so you can also describe dissipation in this model, because the symplectic foliation is given by the hyperbolic sheet. And in fact, the transverse structure will give you a dissipative model for the Poincaré unit disk. And you can also compute this is a Gaussian density for the Poincaré unit disk given by the model of Souriau. To conclude, so I make reference to Baptiste-Coquinot on Morrison for the metriplectic model. But in the metriplectic model, they have made the assumption that the entropy is a Casimir function of the Poisson bracket. It is basic assumption. In the Souriau model, it is by design that the entropy is given by that. Okay, I have given. Yes. So to conclude, you have just to remember these structures behind the thermodynamic, but also behind the information theory and behind the information geometry. You have these structures with two foliation, the symplectic foliation, which are the level set of entropy, and the transverse Riemannian foliation, which are the level set of energy. Okay. So no, just to say that, no, I will, the last slide. The last slide, so this is an interconnection between metriplectic flow theory, Onsager relation, Souriau group thermodynamic on information geometry and foliation. And what is open is to characterize the transverse structures. You have different ways to introduce the transverse structure of symplectic foliation, which are given in these references. So Lieberman foliation on Eifliger gamma structure, transverse Poisson structures, polar foliation on bifoliation, and foliation based also on Helicartan moving frame. So the problem is not closed. Huh? You can work on this problem and to find a very interesting problem. So this topic is we are developing this topic in two European actions. So Caligula, which is a cost action, MSCA action, and Calista, which is a cost action with the University of Bologna. So we are studying different interrelation and especially information geometry and group thermodynamic, and also the application in machine learning. So if you are interested, also we have organized in last September a workshop, Calista workshop at École des Mines, developing this model, and you have different video and slide available on the website, and also you have the talk of Cueto, which gives some illustration and application of Thermodynamics-Informed neural network. And if you are interested, we organize in end of October the 7th edition of GSI, Geometric Science of Information. And the deadline for submitted paper is the 2nd of April. Thank you for your attention.